So we have this asymmetry in the energy principle and the momentum principle. In the momentum principle, definitely, we cannot have the net internal force in a system be anything other than zero. If that were possible, then the system could change its momentum without interacting with the surroundings. And that cannot happen. So this one is always identically zero. But is it the case that a system can never do work on itself? And that is the question which is going to lead us into the discussion of what potential energy is. So let's consider a system that consists of two objects. So here is a planet of mass mp, and here is a moon of mass m. So they're roughly the same size. The planet's a slightly larger one. Let's suppose that they start off at rest. So t is equal to 0, v is equal to 0, v is equal to 0. So here I've got a system which is isolated. So nothing is coming in or coming out. That's time is equal to 0. At time is equal to delta t, these two objects have moved. So the planet has moved some, but the moon has moved more because it's going to have the same force on it, but it has a smaller mass, so it's going to get a bigger change in its momentum. So there's going to be, let's call back the momentum of the moon, the momentum of the planet. Those are the same in magnitude. They have to be because of the momentum principle, so that adds up to 0. Mass of planet, mass of moon. So we have immediately that the momentum of the system in the final state is equal to the momentum of the moon plus the momentum of the planet, but they are the same magnitude and pointing in opposite directions, so that's 0. Great, so there's no momentum in the system. What about the energy? This thing has got some kinetic energy. The energy of the system is equal to the kinetic energy of the planet, so that's momentum of planet squared divided by 2 mass of planet, and the energy of the moon is momentum of moon squared divided by 2 mass of moon. And that is the final energy of the system, but the initial energy of the system is equal to 0. So I do not have, even though it's an isolated system, I do not have the energy in the initial state and the final states of the same thing. So there's got to be something going on here. And what's going on is, if I look at the moon as a system, it's not isolated. It has a force on it in that direction. That's the gravitational force. So there is a positive delta E on the moon. The planet has a force in that direction, and its momentum's in the same direction, so there is a positive delta E for the planet. So there is work that's done on each of the pieces individually, even though there is no work coming from the surroundings. So we can either say that the energy principle is broken, or we generalize the energy principle slightly. So the change in the energy of the system is equal to the work from the surroundings plus the work that's done inside the system. So how can pieces of the system do work on itself? Well, here is exactly a case where that happens. Let me take this work. If the work that's done inside the system has got some special properties, so if that work only depends on the positions of the objects, so it doesn't depend on time directly, and it does not depend on speeds. So a friction force is never going to work here. But things like the gravity force will. I'm going to take this work that's done inside the system over to the other side. So now I have the change in the energy of the system minus the work that's done inside the system is equal to the work from the surroundings. And now I've got, in an isolated system, the work from the surroundings is 0, but the work that's done inside the system is going to come from something else. Delta E system plus delta potential in the system, the interaction energy in the system. So now let's write this, that's equal to 0, and that is sometimes something that you have come across as the law of conservation of mechanical energy. It's a special case of the energy principle when we've got objects in a system which can interact. So the energy of the system let's say, is just the kinetic energy of the two pieces. So I've got K planet plus K moon plus some interaction energy, which is purely gravitational in the final state, minus the kinetic energy of the planet plus the kinetic energy of the moon plus the potential energy of the gravity interaction energy in the initial state is now equal to 0. What we have seen in our little example here, and it's the same one that's in the book, the kinetic energies are not conserved. They change. It starts at 0 and it goes up to some positive value, which means that the store of potential energy that's in this gravity interaction goes down. And that's something that you may have used before if you've taken another physics class, and many of you have. This interaction energy has got different forms. So for gravity near the surface of the Earth, let's suppose we'll set z is equal to 0 as the place where this potential energy is equal to 0. If an object is over here at height z above the ground, ug is equal to mg times z. So it's how high above the ground you are is the gravitational potential energy. For the universal gravitational potential energy, there is the mass of, say, the Earth, and there is u, that you are some distance away from the Earth, r. Your potential energy due to your interaction with the Earth, is equal to minus universal gravitational constant g m Earth times your mass divided by the distance between you. So there's your mass, there's the Earth's mass. Now you might be a little concerned here about this minus sign and this plus sign. These should be the same things. In fact, this one has to be a special case of this one. Let's find out how that could be. Let me make a plot of what this interaction energy looks like for different values of r. So there's r. There is the radius of the Earth. Okay, I've got something which goes purely negative. So there's what the potential energy looks like, purely negative. So this is the interaction energy, U. Now, if you stay near the surface of the Earth, let me make a blow-up of what happens right there on this graph here. So I've got potential energy up. I've got this axis I'm going to relabel as your current position, r minus the position of the surface of the Earth. That tells you how far from the surface of the Earth you are, which also tells you how high from the ground you are. That's the z. So there is this, this part of the curve here is that one right there. And notice you got almost a straight line. This is the same thing as saying that your potential energy increases if you move away from the surface of the Earth. It increases if you move away from the surface of the Earth. These are exactly the same expressions. The only other one that we're going to need is when I've got a spring. So distance r between the two ends of a spring that has a spring constant k. There, the energy that's stored in the spring is going to be 1/2 k r squared. And we can get all of that from a definition of what the work is. Your book goes through that. But these are the things that come from the fundamental statement of what the work those objects are doing is.